So we learn about how to relate the Q, the heat transfer rate, to the area and the temperature differences. And we said that since the temperature differences are changing along the heat exchanger, we should come up with a way to average or take the average of the temperatures. And the analysis showed us that the heat transfer balance analysis showed us that the accurate or the correct way of averaging the temperatures is what's called as the log mean temperature difference. So this is true for both the co-current and the counter-current arrangement, for both the shell and tube and also the double pipe heat exchangers. And I left the derivation for the counter-current to you. And yeah, that's all we had in the previous session. Now, we are gonna learn more about the heat exchangers, and I would like to start my discussion by telling you that there are two types of heat exchanger problems. Okay. There are two types of heat exchanger problems. In the first one, you're given the heat transfer rate or the heat duty, U, the overall heat transfer coefficient, and the log mean temperature differences, delta TLM. Or you're given the temperatures of each stream and you just calculate that and find the area, A. This is called a sizing problem. You basically calculate how large your heat exchanger must be by calculating what should be the area of the heat exchanger or the surface area of the piping. And this is an easy problem. You just use this Q is equal to U delta T log mean times area formula, and you just solve for A, right? The second type of problem is you're given the flow rates of the streams, the hot flow rate, the heat capacity of the hot fluid, the mass flow rate of the cold, the heat capacity of the cold, the inlet temperature of the hot, and the inlet temperature of the cold, and you're given the heat exchanger already, so you have the area of the heat exchanger. You already have one working heat exchanger, but you're asked to find out what the outlet temperatures are. Find out what the outlet temperatures are. And this is called rating problem as opposed to sizing. Okay. In other words, you're given the heat exchanger. You just want to find out if you, for example, like send this stream, like these two streams, what are going to be the exit temperatures of these streams. So you find out how the heat exchanger is going to behave. As I said, the first problem is easy to solve. The second one actually requires an iterative method. Which is tedious. let's say seems to require, because we can find a trick for that. Seems to require an iterative method. The reason is because you don't know two temperatures, like you don't know the outlet cold and the outlet hot. So if you knew one, you can calculate the other, but you have two equations, so you can trial and error and see whether a given temperature actually solves two conditions, because you don't have linear equations. But we can actually find a trick for the second type of problems. For the second type of problem, we can also use what's called as the number of transfer units, epsilon method. NTU stands for number of transfer units. Epsilon is the effectiveness. Effectiveness is nothing but the ratio between the actual heat transfer rate and the maximum heat transfer rate possible. What is Q max? So what do we mean when we say Q max? So Q is Q max when T hot 2 becomes equal to T cold 1. T hot 2 becomes equal to T cold 1. In other words, when the hot fluid reaches the inlet cold fluid temperature, which is never going to be the case, but it's just the idealization to see like what is the upper bound, what would be the upper bound for the Q. So that's or T cold 2 is equal to T hot 1. In other words, the cold fluid reaches the inlet hot fluid temperature. Okay. Okay, but which one is actually, so which one is the one that we're going to take into account? There are two possibilities. If the cold fluid has the lower heat capacity, in other words, m dot CCC is less than m dot HCH. This is total, by the way. Not the specific heat capacity, but the total heat capacity. Yeah, in this case, epsilon is equal to, as we said, Q actual divided by Q max. That's equal to, Q actual is nothing but MC dot CC T cold 2 minus T cold 1, outlet and inlet temperature of the cold stream, the difference between them, divided by M dot C CC, in the case where the cold temperature outlet becomes equal to the hot temperature inlet, T hot 1 minus T cold 1. So we actually, instead of this, we replace it by this T hot 1 in accordance with this formula. Okay, and this is basically the maximum value that this can take, right? That's equal to, after the simplifications, you find that the TC2 minus T cold 1 divided by T hot 1 minus T cold 1. Okay, so that's the epsilon. If, on the other hand, MC dot MC dot times CC is larger than MH dot CH, then the epsilon can be written as M dot hot C hot T hot 1 minus T hot 2 divided by M hot dot C hot T hot 1 minus, instead of T hot 2, we replace it by T cold 2, the cold 1. Okay, and in other words, this is equal to T hot 1 minus T hot 2 divided by T hot 1 minus T cold 1. Okay. And we actually can define the epsilon in a unified version. General definition of epsilon is equal to delta T of the fluid with the lower total heat capacity in the numerator divided by, so this is basically, as you can see, the hot one has it. Here I have the hot one temperature difference. Here I have the cold one, which is lower. Then I have the difference for the cold one in the numerator. In the denominator, it's the maximum possible temperature change in the system. So the reason why I use the cold ones in this case, but hot ones in this case, is the following. You can have like a situation where, for example, where you have this, right? Imagine this is hot, this is cold, right? The maximum possible temperature change in the system, if you actually think about it, it's going to happen. So let's exaggerate the case. Okay, this is the cold. Okay, let's make a counter current one. Let's start from here. Let's go all the way to here. Okay. So as you can see, the cold one temperature here cannot exceed the inlet hot temperature, right? So this corresponds to the maximum change in the temperature. And the maximum change in the temperature only happens for the lower heat capacity fluid, because as you can see, this doesn't change a lot, but this is the one which changes a lot. If this is the other way around, if this one is changing less, but the hot one is changing more, then that means the hot one has the smaller heat capacity because its change in the temperature is much larger. Then you would actually use the change in the hot stream temperature as the maximum possible temperature change, because the change in the cold stream temperature does not correspond to a maximum possible temperature change. That's the reason why we actually took into account two different cases. Okay. So for this analysis, you should first figure out which one is going to be having the maximum possible temperature change. That's the one with the lower heat capacity. Okay. So that's why in the numerator also we use the delta T of the lower heat capacity fluid. So that's our definition of epsilon. Let's go back to our, so how is that going to help? We need to actually wait a couple more steps to realize why this is going to be something useful. Let's go back to our earlier formula, which relates temperature differences to the overall heat transfer coefficient and the physical properties. Logarithm of T hot 2 minus T cold 2 divided by T hot 1 minus T cold 1 is equal to negative UA 1 over MC dot CC plus 1 over M hot dot C hot. This is this equation. Let me just refer. Yeah, exactly. So it's this equation that I'm reusing. Okay. And from here, we have T hot 2 minus T cold 2 over T hot 1 minus T cold 1 is equal to exponential negative UA 1 over MC dot CC plus 1 over M hot dot C hot. Okay. And then let's say if, let's think about one of the scenarios. If the cold fluid has the lower total heat capacity, which means this is smaller than this, which means this is larger than this because it's 1 over, right? And for this one, I want to actually take this thing out of the parentheses, and I want to write something like 1 plus some small number. I'm not going to do any approximation here, but I'm just going to rewrite it by factoring out this 1 over MC CC. Okay. So the simplification would be, we would rather write it in this form, if that's the case. Exponential negative UA over MC dot CC parenthesis 1 plus MC dot CC divided by M hot dot C hot. Okay. Let's call this equation 2. Okay. Now, let us express the hot outlet temperature in the form of the other temperatures. So let us express T hot 2 in the form of T hot 1, T cold 1, and T cold 2 using the overall energy balance. Because that's the simplest equation that relates the 4 temperatures, right? As we dictated in the very first line of the class. M hot dot C hot, T hot 1 minus T hot 2 is equal to M cold dot C cold, T cold 2 minus T cold 1. And from here, you would find that T hot 1 minus T hot 2 can be written as MC dot Cc divided by M hot dot C hot, T cold 2 minus T cold 1. And from here, you can solve for the T hot 2, T hot 1 minus MC dot Cc divided by M hot dot C hot, T C2 minus TC1. Right. Now, substituting this into equation 2 will give this equation. Will give the following. T hot 1, instead of T hot 2, I replace T hot 1 minus MC dot Cc divided by M hot dot C hot, TC2 minus TC1, right? That's the T hot 2 minus T cold 2. So I'm writing actually this minus this divided by T hot 1 minus T cold 1 is equal to exponential negative UA over MC dot CC 1 plus MC dot CC over M hot dot C hot. Okay. Let's simplify the left-hand side. Simplifies to, oops, T hot 1 minus T cold 2. Let's subtract T cold 1 and add T cold 1. So T hot 1 minus T cold 1 minus M dot CCC over M hot dot C hot, T cold 2 minus T cold 1 minus T cold 2 minus T cold 1. So I basically subtracted and added the T cold 1. Since this looks like subtraction, since there is minus here, it's basically addition. Divided by T hot 1 minus T cold 1. That's equal to this divided by this minus this divided by this, right? So you would get 1 minus, you can factor this term out. It's the same. T cold 2 minus T cold 1 times 1 plus mc dot cc divided by m hat dot c hat divided by t hat 1 minus t cold 1. Okay. And as you can realize, this thing is the epsilon, right? Effectiveness. Where is that? Yeah. For the, if the cold fluid has lower total heat capacity, so it's this thing. And the left-hand side becomes equal to 1 minus epsilon 1 plus mc dot cc over m hat dot c hat. Okay, so the left-hand side is equal to right-hand side, so you can write it as 1 minus epsilon 1 plus mc dot cc divided by m hat dot c hat is equal to exponential. I'm just rewriting this equation. Exponential negative UA over mc dot cc 1 plus mc dot cc divided by m hat dot c hat. Right, and from here you can find the epsilon in terms of no temperature dependence, right? So you can calculate it without knowing the temperatures, which is 1 minus exponential minus UA over m dot CCC 1 plus m dot CCC over m dot HCH divided by 1 plus m dot CCC divided by m hat dot C hat. Right? So this is nice because we have found the epsilon by not needing any temperatures, by not knowing about the temperatures. So basically, you have another equation that relates the temperatures to each other. Okay, and there is another quantity here, which is this thing. Let's give it a name. UA divided by m dot CCC, or for this one, since we picked the MCCC is the lowest of all, you can call it UA over m dot C for the minimum value of that. I mean the stream, for the stream that gives the minimum value. We call this number of transfer units. Okay. And the larger it is, the larger the effectiveness. So meaning that the larger it is, you have a better heat transfer going on, right? And so let's do some more definitions here. So let us simplify things by just like changing the variables. Let us define MC dot CC equals to Okay, I want to use, let me use this, yeah, fancy C, let's say, CC, okay? It's just a letter that I made up, M hot dot C hot, let's call it C hot, okay? And C min is the lower of CC and C hot, and the C max is the higher of CC and CH, okay? And then the epsilon takes the form 1 minus exponential minus number of transfer units times 1 plus C min divided by C max divided by 1 plus C min divided by C max for concurrent flow. Okay. For countercurrent flow, the same procedure yields epsilon is equal to 1 minus exponential minus NTU 1 minus C min over C max divided by 1 minus C min over C max exponential negative NTU 1 minus C min over C max this is section 22.4 in textbook. Okay, so 22, just 22, 4. Let me check one thing really quick. Okay, so I recommend you to follow the calculations there, or derivations. Okay, good. So this is about pages, I guess, 376 to 378. Yeah. Okay. So, but how is that going to be useful now? Now we have two equations, right? So if you know the epsilon, now you can actually, you have, that means a linear equation for the 4 temperatures, right? And if you know the 2 fluid temperatures, then actually you can calculate using the epsilon and the energy balance. in the case where one of the two fluids okay, so okay, let's think about the following case. Imagine that one of the fluid is boiling or condensing. Okay, is either boiling or condensing, and you already have this equation, MHCH, TH1 minus TH2 is equal to MC dot CC, TC2 minus TC1. And delta T for the fluid condensing or boiling, you know that it goes to 0 because you probably have no temperature change if it's a pure fluid, implying that the fluid undergoing phase change can be interpreted as having an infinite specific heat capacity right? So, which means that the C max goes to infinity, and C min over C max goes to 0. How does the equation simplify in this case? If you have a look at this, so this goes to 0, this goes to 0. For either case, you have 1 in the denominator. So the epsilon reduces to one minus exponential negative number of transfer units for this particular specific case. Okay, so now let's make sense of what we had so far, what we had done so far. Now, with the number of transfer units method, as long as you know the C min and C max, right, and also the U and A, we can find the epsilon from this equation. And the epsilon relates to 4 temperatures. So using also the heat equation, the heat balance equation, you can solve for both of the temperatures without any iterations, right? So let's summarize it here with the NTU method. As long as C min and C max are known, along with U and A, we can find epsilon, which will relate the 2 unknown temperatures. Right? This, along with the overall energy balance, will provide us with with the unknown temperatures. Without any iterations, right? Right? Any questions so far? Okay. But if you have the first scenario, for example, but if the temperatures are known, finding A, in other words, the NTU, is not straightforward. And in that case, using the log mean temperature difference method will be easier. Okay.